Hey guys, welcome to Wednesday. You guys have a speaker, believe it or not, at 10:20 today, so hopefully you signed up for that and are ready to go with that. So our class is technically a little bit shorter, but it's Wednesday, so you kind of make your own rules anyway. So I'm going to get right to it today. Today's focus is going to be pretty narrow on what we're going to be trying to achieve here. But let me just kind of walk you through where we're going to go. We're going to do 2 demonstration problems, and there's going to be a 4-problem assignment. But we're starting to put the icing on top of this whole chapter here, so I hope that doesn't frighten you. But we've got a couple little things to tackle, little crumbs to pick up here. So let's say you've got an elevator, and for whatever reason, you decided to hang a fish from a scale in this elevator. That's probably not really something that should be recommended, especially if you forget the fish. It's going to be bad for the next people being transported in it. But this fish has a weight of 40 newtons. Okay, so we're going to kind of remember that. It is hung from a scale in an elevator, and this elevator is going to accelerate upward at 2 meters per second squared. So when it does that, what is this scale going to read when this fish initially weighed 40 newtons on this scale? What's it going to read now? Okay, then let's put a twist on it. Let's say the elevator accelerates downward at 2 meters per second squared. So what's going to be happening there? So here's our situation. We're going to draw a free body diagram of this puppy. It has a weight of 40 newtons. But we know that some reason, let's call it a tension T or whatever this force is, that is going to exceed this weight because there's an acceleration this way, so that means that there's a net force operating in the upward direction. Now, again, we wouldn't include this on the free body diagram, but it's there. It's the difference between my tension pulling upward and my weight pulling down. Okay, so if that's the case, let's kind of flesh this out. We're going to look for what does this scale now read. That's what that value is going to be, okay, because that's how hard it's pulling up on the fish. So if I know that that fish normally weighs 40 newtons, the mass of a 40 newton fish is going to be 4.1 kilograms. I'm just going to divide that by 9.8 meters per second squared. And if that's the case, my acceleration is 2 meters per second squared upward. So what I'm going to do here is I'm looking for the force on the scale. And I know that my net force is going to be the difference between the force in the scale and the weight. And I can see that on this free body diagram right here. Okay, I call this the tension, same as the force in the scale. So I'm going to rearrange this because what I'm really looking for is the force on the scale, not the net force. So I'm going to rearrange this, toss the weight over the other side. So the force in the scale equals my net force plus the weight. I'm going to substitute in what I know. I know my net force is the equivalent of MA. So I've got a 4.1 kilogram fish times acceleration of 2 meters per second squared. I know the weight of the fish is 40 newtons. And so if that's the case, the force in the scale is 48.2 newtons. That's what the scale will read as it's accelerating upward. Now, if I want to solve it if it's going downward at 2 meters per second squared, all this then becomes is the fact that my net force is going to be my weight minus the force on the scale. And just as this increased my weight by 8.2 newtons here, it would decrease it by 8.2 newtons if it's accelerating downward. So that would be 31.8 newtons if it's accelerating downward. So that's an elevator problem. I'm going to show you something else here. So here's a second problem. I've got 2 blocks, each with a mass of 3.5 kilograms here. And they're fastened to the top of an elevator. The elevator is going to accelerate upward at 1.60 meters per second squared. And I want to find the tension in the upper and the lower strings. Let's call the tension here T1, and tension here T2. Okay, so watch how this plays out. These are my givens. My acceleration is 1.60 meters per second squared. I know mass 1 equals mass 2 equals 3.5 kilograms. And I'm looking for the tension in the bottom string right here. and the tension in the top string right there. So I'm going to focus first on this bottom string. I know that my net force equals the tension minus the weight. Why do I know that? Because if I were to draw a free body diagram of this, I know that there's a net force because it's accelerating that way. That means that this T1 has to exceed this weight. Let's call it weight 1. Okay? So if that's the case, my net force here, again, I'm not going to write that on my free body diagram, equals T1 minus weight 1. Okay? So I'm going to rearrange this since I'm looking for T1, and I'm going to flop my weight over to the other side here. So my T1 equals M1A, which is my F net. That's the same thing. It's mass times acceleration. It's Newton's second law. And my weight is the same as mass times gravity. So I hope that wasn't too big of a jump to go from here to here, but they're the same thing. I'm just rearranging it. And now I'm going to substitute in what I know. I know that my tension is going to equal mass times acceleration. That's my net force, plus my weight, which is mass times gravity. So I find out that my tension in this first string is 39.9 newtons. So that's great. I know that that T1 equals 39.9 newtons. But when I get to T2, T2 has a lot bigger task because T2 also has to carry this mass in addition to this mass. So how are we going to solve for T2? Well, I know that for T2, my F net, it's still accelerating upward. Here's my second mass. So that means that there has to be an F net going this way. That means that this T2 right here is working against two things. One is working against the weight of this object, and it's also working against T1 because that tension in the string is pulling both ways. If it's pulling up on the bottom one, it's pulling down on the top one. And so my net force here, my T2, is going to equal this net force. I'm just rearranging this equation here. My net force here equal T2 minus T1 minus my second weight. I rearrange that to solve for T2. T2 is going to equal this net force. I rearrange that to call that by Newton's second law M2A plus T1 plus, that's my weight, M2G. I just rearranged that, flipped the others over to the other side. So I'm going to substitute in T2 equals this net force on that mass plus this T1 that's working against me plus the weight, and I'm going to find out when it's all said and done that my tension in the second string is twice as great as the tension in the first string. This string right here is trying to handle twice as much labor as the bottom string. Okay? Now, just to show that this works, I'm going to take you around the table here and show you something. Now, I don't have an accelerating elevator here, but I do have a stationary situation. And so here you'll see that I have two scales. I've got a mass down there of 500 grams. And I have a mass here of 500 grams. I've got a spring scale that's reading right here. And I've got a spring scale that's reading up at the top. Now if I look at the bottom spring scale, you'll see that that is reading 500 grams. And my top spring scale is going to be reading about 1,000 grams. Okay? So you can see this kind of played out here in this situation. So for tomorrow, that's what I want you to tackle. They involve the two types of problems we showed here. Okay? And we will see you on Thursday. We'll start Doomsday prepping for a test on Friday. We'll talk to you guys later.